x plus 5 times 2x minus 1 over x plus 5 times x minus 1. What we want to do is we want to use limits to establish our horizontal asymptotes, our holes, and our vertical asymptotes. So for the horizontal asymptote, we're going to let x go to positive infinity. And what we can do is those terms are going to cancel. So we can compare the largest power terms. And since the powers are the same, the ratio of the powers is going to be the limit as we go to positive infinity. So formally written, we just say that limit as x goes to positive infinity is equal to 2. If we let x go to negative infinity, we get negative over negative, which is positive. So it's also equal to positive 2. And so now what we've done before, we did this before without limits. Now we're just doing it formally with limits. So I can draw my horizontal asymptote in both directions at y equals 2. So before we establish holes as well, but we're going to do this using a limit. So since the terms cancel out, okay, we do have a restriction there, and we can't actually let x equal 5. But we could predict what the y value equals when x equals 5 by just plugging into the expression. But to do this, we need to formally write a limit, which is what we've done here. So when I plug negative 5 into the expression 2x minus 1 over x minus 1, I get negative 11 over negative 6. That simplifies to 11 over 6. So what does that mean? It means that we have a hole at that point. So the hole has a coordinate of x equals negative 5, y equals 11 over 6. And so if negative 5 is maybe about here, this is just below the asymptote. So there's this issue of the vertical asymptote as well. The vertical asymptote is when the factor doesn't cancel. So we know we have a vertical asymptote at y equals positive 1. So drawing in my vertical asymptote of positive 1, there it is, I need to establish my limit as x goes to 1. Well, as a two-sided limit, the limit does not exist. However, as I approach it as a one-sided limit, okay, from the left-hand side, what I'm going to be doing is I'm going to be plugging in numbers to the left of 1. So for example, 0.9. If I were to put in 0.9 into that, I end up with the denominator approaching, it's going to be negative 0.1. So it's going to be approaching 0 from the negative side. So I'm going to write this divide by negative 0. Although there's no such thing as negative 0, I'm approaching 0 from the negative side. For the numerator, I'm just going to plug in the value of x equals 1. So I get 2 times 1 minus 1, and that gives me positive 1. So what this means then is I'm dividing by 0, so I'm going to get infinity. And since I have a positive divided by a negative, it's going to go down to negative infinity. So it's going to follow my asymptote, go through the hole, and then it's going to go down to negative infinity as my asymptote. Okay, so that's what that part of the graph is going to look like. Then we establish what's going to look like on the other side as I approach from the positive side. So if I'm approaching from the positive side, I'm plugging in values to the right of 1. So for example, 1.0001. What ends up happening is I get 1 minus 1.001 minus 1. I end up with a positive 0.001. Or in other words, I'm getting numbers close to 0 that are positive. So I'm approaching 0 from the positive side. In the numerator, I'm going to plug in x equals 1. So I get 2 times 1 minus 1. Again, I get positive 1 in the numerator. I'm dividing by 0, so I'm going to get infinity. Positive over positive gives me positive infinity. So what that means is I'm going to follow my horizontal asymptote, and as I approach my vertical asymptote, it's going to go up to positive infinity. So we've done this before without limits, but now we are using limits to do this formally. So we're just formalizing what we've already done and using the limit notation to show how we get these different points: horizontal asymptotes, holes, and vertical asymptotes, and showing the directionality can be found by looking at one-sided limits.